Hello everyone. In this video I am going to show you some of the examples from chapter 3 which is actually equilibrium of a particle. So before starting that, let me summarize the theory which you already learned, that if you have multiple of forces working in a single point or a single particle, then basically and the particle is in equilibrium, then basically the summation of forces in x direction equal to 0, summation of forces in y direction equal to 0, and that means like the summation of force in every direction equal to 0, right? But we formally write that one, that summation of fx equal to 0 and summation of fy equal to 0. Now I also want to talk about a little bit about the structural member that we have been using in these chapters. You can see, let's say this is a steel beam. So you can see, if you take that steel beam, try to pull, you cannot. Try to push, you cannot. And when you try to bend, you will see that this one will offer significant resistance for bending, right? So for any rigid, we call that one rigid member. For any rigid member, basically you have three components of reaction, which is tension, compression, and bending moment, okay? How about, like, you will see in this chapter we are going to use a lot of this type of members, which is here I'm showing you a chain. It could be cable or other like elements. You can see they can only, if you try to pull that one, they will offer significant resistance for that. But if you want to compress that one, then they will compress. Similarly, if you want to buckle any chain, they will easily buckle. So they don't offer any resistance to compression or bending. That's why we don't use these members for compression or bending. We only use these members so that they can take tension. Like we can make a swing, or we can hang something with the rope or cable, because they can take only tension, okay? We can also see that we are using springs here in this chapter. So if you apply any load F here, then basically you will see this one will move from here to here. And if this distance is x, then basically F is equal to Ks. And K is called the spring constant. And one more component you are going to see here, frictionless pulley. Okay, these pulleys which we are going to use in chapter 3 is basically frictionless pulley. This means like they have like a lot of bearings here, and they provide very insignificant frictional force there. So if you are using any pulley, then you can see this is a rope going over the pulley. So if you have tension T here, this tension also T here, because this pulley is not going to change the magnitude of the force. It's only changing the direction of the cable, okay? So you have to remember, if you have like same rope, then you have actually same tension that passes through the pulley. But the pulley can only change the direction of the cable, okay? So that's the basic thing. We have to deal with that. Now let's try to show a easier problem first, and then we'll move forward, okay? So here, this is your problem number 2-6. We are gonna solve that one right now. You can see three different forces is working at this point here, okay? So the first force is 8 kilonewton coming this direction. 9 kilonewton this direction, and there is a force here which is called T. I don't know the magnitude of that force, and this one is asking like what angle this one is making with your angle here, with this force here. Okay, they're asking you what is theta and what is angle and the magnitude of this force. Okay, now let's say I already know this angle here. This angle, let's say alpha, which would be tan inverse 3/4. Okay, and let's say this angle is phi. So theta is nothing but alpha plus phi. Okay, now since this one is in equilibrium, we are just going to use the summation of force in the x direction equal to 0 and summation of force in the y direction equal to 0. So let's start with summation of fx equal to 0. And this is your positive direction. Most of the time we try to show that one at the top of the equation, that which one is positive, which direction is positive. So if you see, then basically this one doesn't have any, component in the x direction. The t cosine phi, and then you can just see the horizontal component that's actually working this direction. That's 4/5 of the force 8 kilonewton. That's equal to 0. Okay, so I can simplify that one. T cosine phi is equal to 5. Let's say this is equation number 1. Similarly, we can write equation number 2, which is summation of fy equal to 0. Let's say this is positive direction, upward. So you can see this is 9 minus this one here. So the vertical component is 3/5 of 8. And then this one is t sine phi, which is working downward, so negative. So again, I can simplify this equation like this. So t sine phi is equal to 9 minus let's say this is equation number 2. Now I have to, you can see in these two equations I have two unknowns. One is t, the other one is phi. Okay, so if I divide equation number 2 with 1, 2 divided by 1, then basically I see this one would be so you can see this one is basically t cancels, and sine phi divided by cosine phi, that's actually 10 phi, okay, let me write it here. (21/32), so phi equal to tan inverse that's basically 33.27 degree. Now if you plug the value of phi in any of that equation here or here, then basically you can find out the value of t, which is basically 7.66 kilonewton. Now they ask you to find out the theta, so this one is alpha is basically tan inverse 3/4 plus 33.27, that's basically 70.1 degree. So that's basically your answer here. Okay, let's move forward. Problem number 3-8. Okay, this one is saying basically that the chord ABC, that's A, B, C, this chord here, or chord BD can support a maximum load of 100 pounds. Determine the maximum weight of the crate and the angle theta for equilibrium. Theta is basically this angle here. So basically it's saying that this body is in equilibrium, and try to find out the maximum weight you can hang here so that none of these three cable has more than 100-pound tension. Okay, now first we will try to draw the free body diagram here. So if you cut that rope here, cut that rope here, and cut that rope here, then basically let's say this is your W. Since this is the same rope here, this one has to be W2. And you know the direction of this one, which is 12, 5, 13. And this one is actually your, let's say, T1. Okay? So now you can see here that I have 1, 2, and 3 unknowns here. Okay, and I have 2 equations, summation of fx and summation of fy. So I cannot solve 3 unknowns from 2 equations. So what I have to do, I have to assume that, like, let's say for here, I'm assuming that T1 is basically 100 pounds. And then I'll check that what is my W here. If my W here is less than 100, then basically my assumption is okay. If W is more than 100, this means like none of the cable will take more than 100 pounds, so my assumption is wrong. So I have to start assuming this one is W. This one is 100 pounds, okay? So first I'm assuming that T1 is 100 here. Now we'll start like the summation of forces. Here I'm going to start with summation of forces in the x direction. So you can see here that this one, the horizontal component of this W is 5/13. That's actually positive. Sorry. Minus that 100 cosine theta is equal to 0. So I can rearrange that one, or I can say 100 cosine theta is equal to 5/13 of W. Now I can get the summation of forces in the y direction. So you can see here that 100 sine theta minus W minus 12/13 of W is equal to 0. Okay, so if I rearrange this one becomes 100 sine theta is equal to 25/13 W. Now I assume this one is equation number 1 and this is equation number 2. So if you divide 2 with 1, then basically you get 100 sine theta divided by 100 cosine theta is equal to so this one cancels and you see this is actually tan theta is equal to 5. So your theta would be tan inverse 5. That's actually 78.7 degrees. Okay. Now you can just plug this value of theta, either equation 1 or equation 2, and you can find out your W, which is actually 51 pound. So plug the value of theta in equation, let's say 1, and from there you can just find out your W is basically 51 pounds. Now check that one, that actually your W is less than 100, right? So your assumption is okay. So this one has 100 and this one has 51 here. So your assumption is okay. So basically your answer is this. Okay, let's move forward. Problem number 3-36. Okay, this one is saying determine the mass that you can hang here so that this point will sag from here to here, which is actually 0.5 meter. So you have to find out the mass here. Okay, now you can see this is the initial length of this spring here. Let's say this is L, and this is L initial, and let's say L final here. So if you use the Pythagoras formula, then basically you can find out the length of L1 is basically Li is basically that's basically 2.5 meter. Now after hanging this one, you can see this one has changed from here to here, and the LF is basically now 2, and here is 2. Which is basically 2.828 meter. So the del S, which is LF minus, or I can say S, the change in length, S is equal to final length minus initial length, which is 2.828 minus 2.5. Now if you want to find out the force here, then the force is always Ks. So Ks is 100 multiplied by this S here. And then we can get that this is actually 3.28. $38.8 actually Newton. Okay, that's the force working here. Now if I draw the free body diagram of this one here, then you can see so this one is 32.8 Newton, and you can see this one is actually 45 degree because this is 2 and this is 2, so this angle is 45 degree. So if you take the summation of forces in the y direction, so this force here, when I express that one with force, then basically that's m multiplied by 9.81. So you can see summation of Fy equal to 0. So you can see 32.8 Newton and sine 45 degree minus m into 9.81, that's equal to 0. Okay, so if you solve for m, then basically your m would be 2.37 kg, 2.37 kilogram. Okay, Now you can ask that question like, how about this one? Basically this one is actually symmetric, this side and that side. So I don't need that one, to do that, because that would be the same thing here. That would be also 2.37 kg in the other direction. If this sag is different, then basically you will see the answer will be a little different here. Okay, let's move forward. Problem number 3-27. That's a little bit longer problem, but not that difficult at all. You can see they're asking here that each cord can sustain a maximum tension of 500 Newton. Okay? Determine the largest mass of pipe that can be supported. So you have to support like a weight here, so that none of the cable here that can exceed a tension of 500 Newton. So basically what we have to do, we have to find out the tension each of the cable in terms of W, and see that which one has the highest tension. So on the highest tension, I'm going to set that one as 500, so all others would be less than 500. Okay, now let's move forward. We can start from this point here at A. This is actually point A here, and this is point B. So if I draw the free body diagram, I'll just cut it here and show that one F or T A E. I'll cut it here, so this one is basically equal and opposite. Then you can say write that one T A to B. So that's also T A B. Okay. Now we'll try to focus first the free body diagram for this one. Once I get the TAB, I'll just plug that one here because this is the same rope, and then find out these two here. Okay, so for this one, let me start with, let's say, summation of Fy equal to 0. So you can see TAB sine 60 minus W equal to 0. So TAB is basically W by sine 60 that's basically 1.15 W. So I'm just trying to keep everything in terms of W. Okay. Now let's try the summation of forces in x-axis. Force so you can see TAB cosine or TAE minus TAB cosine 60 is equal to 0. So TAE is equal to TAB cosine 60, so that's actually, I can plug the value of TAB, which is 1.15 W, and the value of cosine 60 is half, so That's actually 0.57. So I got the TAB, which is 1.15 W. So I have the values here for TAB, and that's actually TAE. So I'm going to delete this part here. I'll just keep that one so that you can see in future. Now I'm going to work, I can take this one off too. I'm going to work this one here. So this one is, let's say, TBD. And this one is TBC. And again, you can see this is basically, this angle is actually 30 degree here. And this angle is 60 degree here, okay? Now, if I take the summation of forces in X and Y direction, then basically I'll be able to find out TBD and TBC here, okay? So let's say summation of forces in Y direction first. So you can see 3/5 of TBD minus 1.15 W. This is cosine, so this one is sine 60. That's equal to 0. So from there, you can find out your TBD, which is 1.15 W sine 60, and you can see this is 5/3, which is basically TBD 1.667. W. Similarly, you can just find out this one here. So summation of Fx equal to 0. So TBD, that's actually 4/5 of TBD. And then plus 1.15 cosine 60 minus TBC equal to 0. So TBC is equal to 1.91 W. So now I know the tension for each of the cables. You can see this one is 0.57, this is 1.15, this is 1.91, and this one is 1.66 W. So which cable has the highest tension? Definitely this one. Whatever is the value of W, we can see that this one is 1.91, which is higher than any other tension in any other cables. So this one is the highest. So I'll set that one as 500 Newton. So if I set that one as 500 Newton, which is equal to 1.91 W, so your W would be 500 divided by 1.91. That's 261.7 Newton. Or if you want to express that one in mass, then basically if your mass is M, so that would be 261.7 divided by 9.81. That's actually 26.7 kg. Okay, so it means like if you hang 26.7 kg, then basically this one would have 500 and all others would be little less than 500. Okay, so that's the answer, that you can hang like this much here, this many Newton or this many kgs. Okay, let's move forward. Problem number 3-36. This problem is a little bit difficult, okay, but if you were good at geometry, then it would be okay to do that one. Now this one is saying that cable ABC has a length of 5. So ABC, this one has a total length of 5. Determine the position X and the tension developed in ABC required to equilibrium of the 100 kg sac. This is 100 kg here. Neglect the size of the pulley at B. Okay, so neglect the size of the pulley at B. So you have to find out this distance and how much you have to put that one here to have something like this. Okay, so first of all, here this is the point B. You can see the weight is working here, which is 100 kg. So that's actually 100 into 9.8. That many newtons. So for this particular one, first of all, I can just try to say like summation of Fx equal to 0. So you can see T cosine theta is equal minus, let's say minus T cosine phi is equal to 0. So from here you can see actually theta is equal to phi. Okay, so this angle, two angles has to be same. So let's change that one to phi here now. Now if I take the summation of forces in the y direction, that's also 0. So you can see actually 2t sine phi minus 100 into 9.81 is equal to 0. Okay, so um, I'll just keep that one as equation number 1 and try to solve uh, this figure here based on the geometry so that I can find out the value of t there. Okay, so maybe I'll just write it here. 2t sine phi is equal to, actually I'll just write this one, t sine phi equal to 50 into 9.81. That's equation number 1. Now in this figure you can see this is your x, the total is 3.5 meters, so this one would be x, this one would be 3.5 minus x. Now you can also see, since this one is phi, so this one has to be phi. Again, if this is phi, this angle is also phi. Now just for clarity, let me take this one off from there. Let's say this distance, this length from here to here is L1. This length from here to here is L2. This length from here to here is L3. And this is L4. Okay? Now you can see as given that L1 plus L2 is basically 5 meters, right? So first of all, L1 plus L2 is equal to 5. Now what is L? L is x divided by cosine phi, right? L1 is actually x divided by cosine phi. And L2 is actually 3.5 minus x divided by cosine phi. So if we add this one, basically you can see 3.5, actually let me write that one, plus 3.5 minus x so x cancels, so 3.5 by cosine phi equal to 5, or cosine phi equal to 3.5 divided by 5, so phi equal to cosine inverse 3.5 divided by 5. That's basically 45.57 degree. Okay, so this one is phi is 45.57 degrees. Now you can also see from here the L here, like L3 plus 0.75, that's actually 0.75 here. So this plus this is equal to L4. Okay, so L3 is basically x tan phi, right? So This one is x tan 45.57 plus 0.75. That's basically L4. L4 is the part of this triangle, so you can see that would be 3.5 minus x 10 feet. Okay, so you can see there is only one unknown here, which is x. So you can solve that one. So your x is basically 1.38. And again, if you just plug that value here, t sine 45.57 is equal to 50 into 9.81. Then basically you can find out the value of t, which is 687 Newton. Okay, so that's basically your answer. Actually, this too is your answer here. Okay, it's a little bit difficult, but you have to remember the geometry, that this plus this is equal to 5, and this plus 0.75 is equal to this one here. Okay, now I'll just try to stop for 2D problems here, and in another video I'm going to post you for 3D cases. Thank you.